My name is Ardi Aidini. I am a student at the University of Illinois at Springfield, and today we're going to be doing spectra analysis of mass spectroscopy, IR, carbon NMR, and proton NMR. So the chemical formula of the compound that we are going to be observing today is C6H11O2Br. And we're going to begin by first observing the mass spectroscopy graph that is shown here. And the way we read this graph is from the right-hand side to the left. So we start by first finding the M plus value of this. So we're going to know that the M plus value is the value that is at the very right-hand side. So here it's clearly 194. But you can also calculate this by just finding the molar mass of all the elements that are in your formula, and that's also going to equal the M plus value. So then we're going to move on to the base peak. And this is the value that is highest up on this chart here. So it's going to be 115. That is our base peak. Next, we're going to look at some fragmentation that can occur from this. And so we can see this by taking 194 minus 177, which is this value right here. And we're going to get that we have an M17 fragmentation pattern for this graph. And then we're going to have to solve for the degrees of unsaturation. And to solve for this, we are going to use the formula 2C plus 2 minus X minus H all over 2. And so the X here is going to stand for number of halogens that are present in your compound, and clearly we have one over here, which is bromine. And then H is going to stand for the number of hydrogens, which we have here is 11, and the C is obviously standing for the number of carbons, which is 6. So put some numbers to this. We're going to get 2 times 6 plus 2 minus 1 minus 11 all over 2. And this is going to end up being 1. So the degree of unsaturation turns out to be 1, which means that we could potentially have a pi bond, or we will have a pi bond in our structure of this formula. And also it is important to note that we do have a bromine in our chemical formula here, so that's also going to be something we need to keep an eye out for as we move forward in this analysis. Next, we're going to move on to infrared spectroscopy. And here we have 5 zones, and each zone is going to have its own functional groups that are associated with it. And so if you're not very familiar with these, this is a great chart here that shows each zone and each functional group that could be a part of that zone. So by looking at our data here for our molecule, we can see where some of these peaks are, and we can start putting functional groups to these peaks. So zone 1 was from at a wavelength of about 3200 to about 3700. So that was going to be zone 1. Zone 2 is going to be from about 2700 to about 3200. So this is going to be zone 2. Zone 3 is from about 2000 to 2300. So here to here, that's zone 3. Zone 4, we have from about 1600 to 1800. Then we notice we have something very sharp there. So that's zone 4. And then zone 5 is from about 1600 to 1400, so about here. So in zone 1, we can have functional groups such as amines, amides, alcohols, and things of that nature. And we do have a dip here. However, it's not extremely sharp. Like if we had an alcohol, it would be something like this, but we don't notice that here. So we're going to just keep the alcohol on the back of our mind, but we're going to move on to the second zone to see if we can get something more evident. So here we see that we have a rather deep fang, and this is very evident of a carboxylic acid. So that's going to, carboxylic acid is a possibility here. In zone 3, we notice that we don't have any peaks, so we're not going to have anything there. Zone 4, we do notice that we have a peak here, and this could very well mean that we have a carbon double bonded to an O. And in zone 5, we see that we don't have any peaks, meaning we won't have functional groups such as alkenes. And we also notice that we didn't have any peaks here in the third region, so we know we're not going to have any carbons triple bonded to another carbon or nitrogen or anything of that nature. So we're not going to have any of those in our structure. And then we can also completely discard the area from about 1500 all the way to the right, because this is known as the fingerprint region, and we do not pay any attention to this, as it is not beneficial to helping us solve for our structure. So now we can review all of the possible functional groups that we can have in our structure. So we noticed here in zone 1 that a possible alcohol, O bonded to an H, is a possibility. We see that we have a carbon double bonded to an O. And so these two functional groups give pretty strong evidence that we could have a carboxylic acid in our structure. So that looks something like this. And we did see a sharp peak here, so there's a very, very high possibility. So now we're going to examine proton NMR, where we can get a good idea of what our structure can and will look like. So let's recall our chemical formula of the compound we were observing, which was C6H11O2Br. On the left-hand side, here we have a potential formula or a potential structure for that formula, where we have 6 carbons, we have 11 hydrogens, 1 bromine atom, and 2 oxygens. Now, proton NMR can help us because it shows the integration numbers, which are shown right above each of these peaks, and also shows the splitting of these. However, in this specific example here, we can't really tell exactly what the splitting is because it's hard to tell. However, if we were to examine these splitting pattern further with a image that is zoomed in, we would notice that each of these peaks here that has an integration number of 2H, is a triplet. A triplet, which means that each carbon environment is going to have 2 hydrogen atoms adjacent to it. So we're going to have CH2s. Also, the integration numbers give us an idea of how many protons that we're going to have in our structure. So as we can see here, we have 2, 4, 6, 8, 10, and then we have 1 all the way over here, so 11. And from our formula, we see that we have 11 hydrogens, and we have all 11 hydrogens accounted for in this structure. So next we'll examine where these peaks are within our structure. So basically, electronegative atoms or functional groups, the environments that are closest to the most electronegative functional groups are going to be shifted downfield the furthest. So a good example of this would be this hydrogen, which is right down here. This hydrogen is directly attached to this oxygen here, so it's going to be shifted downfield the furthest. The next environment, we'll see that this CH2 right here is attached to a bromine, which is also very electronegative. So that's going to be this group right here. So then this environment here, since it's not directly attached to the carboxylic acid or the bromine, is going to be the least shift it to the left, so it's going to be that one there. And then we can follow this pattern and see that this environment would correspond with this here, and that this environment will correspond with this here, and this environment here will correspond with this. And this is a guide to proton NMR chemical shift values, which can be really beneficial to make sure that you have the correct structure and you have the correct functional groups that align with the peaks that are shown in the proton NMR graph. So next we will analyze carbon NMR, and it is important to note that for carbon NMR, the peaks that are shown on this graph, so as we can see here, we have 1, 2, 3, 4, 5, 6 peaks, is going to correspond with the number of carbons that are present in your structure. So if we recall, our structure had a chemical formula of C6H11O2Br, so clearly the 6 carbons correspond with the peaks that are shown here. So then we're going to observe how far downfield each carbon environment is shifted. And this will all be relatable to the carboxylic acid here, which is very electronegative, and it forces environments to be shifted downfield furthest the closer you are to this environment. So we can see that since this group here, this carbon group here, is the furthest from the carboxylic acid, we can say that this is going to correspond with number 1, which was here, so number 1. And then this environment here is going to correspond with number 2, because it is shifted slightly downfield, and that would make sense because we are getting closer to the carboxylic acid. And then number 3, we're going to give this value, because again, we are getting closer to the carboxylic acid. And so following that pattern, we're going to get this to be number 4. Number 5 is going to be here. And so for the sixth carbon environment, we see that it is here, and it is directly bonded to the oxygen via the double bond here, and bonded to this alcohol group here. So we would expect this carbon to be shifted downfield the furthest. So we see that this is going to be right here, which corresponds with number 6. So we will say that this carbon here will be shifted downfield the furthest because it is attached to those electronegative oxygens. And this here is a guide to carbon-13 NMR chemical shift values to help you understand where the carbon environments are on the peaks that are shown and help you relate them to your structure. So carbon-13 NMR is essentially the last step into verifying that the structure you have formed is the correct one of the given chemical formula that you were initially given. So that is all for this video. Thank you so much for watching.